Okay, so this is the last of the videos for this special type of kinematics, this two-dimensional motion. So this is what happens when we launch it at an angle. Okay, so when a projectile undergoes this type of motion, it resembles like a football being kicked or a car being jumped off a ramp. Excuse me, a soccer ball being kicked, a baseball being thrown, a basketball being shot, a cannon being shot. Okay, so the thing is though, is that it's going to be directed up towards a specific point. Okay, so the path that it takes, is panning, not penning, is what is called the trajectory. Okay, so this is the path it takes. Now the shape, and this may be a question that pops up in a multiple choice, but the shape is a parabola. Okay, so there's a difference between the shape and the path. The path is trajectory, the shape is parabola. Okay, so if I have, let's say, my cannon down here to being fired, so what does the path look like when it's launched at an angle? Okay, well, it's going to look something like this, right? And so what we're going to talk about, and we break down some of some of the terms. So what's going to happen is we're going to have an initial velocity launched out at an angle. Okay. Up here, which actually occurs at the midpoint, especially if it goes from like ground to ground or original height to initial height to initial height. Okay, and it happens at the halfway point. It's something that we call the maximum height. Okay, now this is a little bit different if we're kind of going from ground to height, right? So if we're doing something like this, so if I'm going from the ground to the height, so like if it's a golf shot, or if I'm going, from up to down, it's not good. This is, yes, technically, mathematically, it is still the halfway point, but in terms of the physics, it's not quite the halfway point, okay? Because these would extend back, this would extend forward, okay? So where it lands is not going to be double the distance. Now here, right, if it's going from original height to original height, then yeah, it's going to end up being the double point, okay? And the great thing about these problems, if you understand parabolas, right, in math class, you can use some math techniques here as well, okay? All right, so the path of projectile that was launched at an angle, okay, it is parabolic or a parabola, okay? The turning point is what we call the maximum height. Now, if you remember when we talked about free fall and we threw the object up, right, when we did this, right, we talked about this point right here too. Let me just redraw this so it's a little bit more understood. Okay. So when I threw it up, I went like this. I had initial velocity. It reached this maximum height, and then it came back down. Okay, and you just have to remember the maximum height. Special things happen, right? So at this point, the object will stop moving vertically, but it continues to move horizontally. Okay, so the velocity vector at the top, and this may be something that you see on, multiple choice questions. So the velocity vector at the top will just be I'm putting this as initial velocity. Okay, so the velocity vector at the top will just be the horizontal piece. Okay. Now, you do have to also remember another thing they may ask about is what is the acceleration at the top, okay? The acceleration along the whole point is a, right? It's a sub y, really, okay? Which is that negative 9.8, okay? And that's true around any point, okay? So if the acceleration also stopped here and the velocity stopped here, the object would just kind of like fall down, okay? So you do also remember we have that saying, right? Time to rise equals the time to fall. Okay, so this idea of symmetry, right? We talked about it in free fall. We talk about it again here, right? Symmetrical. It takes 2 seconds to get up to the maximum height. It'll take 2 seconds to come down from the maximum height. Okay, so and at this point, as I mentioned before, the acceleration is pointing downward, right? So the velocity is pointing in the direction of the horizontal motion, but the acceleration is pointing downward. Okay, now special things also happen here. So if the two objects are launched with the same initial velocity and their angles add up to 90 degrees, they'll land at the same spot. It's pretty cool to see this happen in lab. Now, what really happens is one's going to travel more vertically while the other's going to travel more horizontally. It doesn't mean that they're going to land at the same time, right? Notice not the same time. Okay, I'm going to point that out. It's not the same time. They'll land at the same spot. Okay, so in the absence of air resistance, the optimal launch angle is 45 degrees. And if you talk to anyone in field artillery in the military, they'll probably say 37 degrees because that's when you factor in air resistance. Okay, so the one launched at an angle greater than 45 degrees will take longer to get to the landing point. The projectile, again, will land with the same range or horizontal distance, but at different times. Okay, so angles such as if I launch at 30 degrees and 60 degrees, right? 27 degrees and 63 degrees, 47 degrees and 43 degrees. These will all land on the same range, but this will take longer. This will take longer. This will take longer because they go more up than out. Okay. Now let's break down the formulas before we do some example problems. Okay. And I'm gonna have to write some information over to the right. Remember, your acceleration in the x direction is always 0. Here, your acceleration in the vertical direction is always that negative 9.8. The reason why we're doing that is because we have to add in one extra thing. Okay. So the first thing, and we're going to put it here in the first box, the first thing you have to do is break apart that initial velocity vector into components, okay? Because now we have pieces of the initial velocity that are what the object is being traveled out at, okay? So that's just basically a right triangle. So we're going to do some right triangle trigonometry here. And so the initial x velocity will be VO cosine theta, so whatever the initial velocity is times the cosine of the angle. And the sine, or the y direction will be VOY is VO sine theta, okay? But again, nothing changes, right? So this will also end up being our Vx, our final velocity, okay? Because remember, constant velocity, there's no change in the velocity, okay? Which then our other equation is just going to be that VOXT, right? But then you can just substitute in this VO cosine theta if you're feeling more advanced, okay? But oftentimes you'll solve for this, right? But you have to find t in the y direction, okay? Now the y side, right? We have our initial y velocity. So if we just keep going and using our equations, so our final velocity at any point will be our initial velocity minus 9.8 t. Again, you can also use 10 here if you want. You can use so Vy squared equals V initial in the y direction squared minus 19.6 delta y. Okay. Now this one right here brings in your symmetry as well, right? Remember, we always talk about symmetry, and here's why. Because if I plug it, if I have 2 points, right? If I land in the same position, this part will go away, telling me that my initial velocity will just be my final velocity will be just my initial velocity, okay, in the y direction. And then the next one is kind of the most important formula, and I'm going to write it expanded out because this is where some of your math techniques may come into play. Okay, if you understand parabolas in math, you can use this equation right here to solve for t. Okay, but I also want to point this out: the maximum height regardless of what's happening in physics, is the vertex of that parabola. Okay, so this is physics. That's what we call it. And then this is math. So I'll give you a little hint. To find the y coordinate at that point is going to be negative b over 2a. If you remember, this is a, this is b, right, and that's c. Okay, but here's where the negative b over 2a, where it also comes in, is right here. Okay, that if you solve that out, that's what you get, negative b over 2a. Okay. All right, so let's look at, I think this is the only problem I have, because, I mean, if you can undo this, you can pretty much do all the other problems. Okay, so we have an object launched from the ground at 50 meters per second at 28 degrees and later returns to the ground. Find its max height, time to reach the maximum height, total time of flight, and horizontal displacement. Okay, all right, so here's what step one when you do these problems, right? Break down V0. Okay, so we need V0x, V0y. All right, so we're going to V0 cosine theta, V0 sine theta. Okay, where this is my V0, this is my theta. Okay, so we're going to do 50 cosine 28, 50 sine 28. Okay. So 50 cosine 28 is going to be 44.1, and then 50 sine 28 is going to be 23.5. Okay. Step 2, write the displacement formulas. Okay, so for the x, it's going to be delta x equals VOXT. All right, and for delta, or for y, we're going to do y equals y0 plus VOYT minus 4.9 t squared. Okay? All right. Oh, I meant the pan, not the pen. Did it again. All right. So now we're going to fill in our numbers. So we're going to get, really it's going to be x equals 44.1 t. Okay, here we're going to have 0 equals 0 plus, and guess what? You can, I mean, I know it talks about max height first. In fact, if we just don't call this 0, we call this y. All right, so y equals 0 plus 23.5 t minus 4.9 t squared. So I mean, there's all kinds of paths you can take here. You can go max height first, then total. You can go total, then max height, because this is symmetrical, right? Because it's going to go from ground to ground. So I'm going to start here, I'm kicking it, and I'm going to land here, right? So I'm going from ground to ground, right? So I can either take this equation and find all my max height information, or I can take the equation and find all my final position stuff, okay? Because time-wise, right, this t to get up to the max height equals the t to fall from the max height. So t up equals t down, okay? So if I find this time here, if I find t total, right, well, t up and t down are just going to be t total divided by 2. Okay, and now this is where math comes into play. I don't even know, if I'm given an equation that looks like this, and I'm asked to find t, you have a couple paths, just like when we talked about free fall, right? You can factor, you can use quadratic equation, and if it's a non-free response question, you can use your calculator. Okay, but on test days in the classroom, you're going to have to show your work, so you're going to have to use one of these two. Okay, Now, this one is actually easy to factor. So factoring means I'm going to set my final position equal to 0. Okay. So what happens is, note that both of these have t, right? So I can factor out a t. Here's my factor method, right? So I'm going to do 23.5. I factor out a t from 23.5. I just have 23.5. Factor out a t from 4.9t squared. I have 4.9t. Okay. Now, this is multiplication. Well, when does multiplication equal 0? When either this equals 0 or this equals 0. So t equals 0 or 23.5 minus 4.9t equals 0. Right? It's the only way you can 0 is one of your terms that you're multiplying is equal to 0. Well, this is our starting point, right? This is where we launch from. That's our t equals 0 right there. Okay? So now all I have to do is solve this for t. So I'm going to add over 4.9, and then I'm going to divide by 4.9. So t is going to be 23.5 divided by 4.9. Now, when I do this method, I'm finding the total time. Okay? So it's going to take 4.8 seconds for what I think what they're calling this is what we just found was part C, what they call the flight time. So in physics, they'll call it flight time, hang time, total time. Okay, so we actually found part C first. Okay, now the time to get to the maximum height is our total time divided by 2. Okay, so we're going to do t total divided by 2. So we're going to do 4.8 divided by 2. So our max height time is going to be 2.4 seconds. Okay, so that is our part B. So for some of these questions, you can answer these questions like completely out of order. So notice we did part C first, then we did part B. Now we can do part A. All right. So part A, and notice how I'm kind of working my paper here. Right? How am I working my paper? Well, I have a horizontal and a vertical side, right? So that's my vertical side. So notice I've been working on the vertical side this whole time. Okay? And again, I mean, these problems you can do, there's multiple paths to answer these questions. So now I can go back and I can do part A. Right? So I'm going to say y equals 23.5 t minus 4.9 t squared. Right? Now, how long did it take to get up to my maximum height? 2.4 seconds. So I'm going to do 23.5 times 2.4 minus 4.9 times 2.4 squared. So my max height, y max, again, this is going to be measured from the ground. 23.5 times 2.4 minus 4.9 times 2.4 squared. I'm going to get a max height of 28.2 meters. So there's my answer to part A. Okay, so the last part is just simply part B, or sorry, this is part D, sorry, part T. So part D is now taking our, what is our range, or what is our horizontal distance traveled? So that's going to go back to our total time. So it's going to go back to this 4.8 seconds. So I'm going to say x equals 44.1 times 4.8. And so that's going to be equal to 44.1 times 4.8. And we get a total of 212 meters. Okay. So just to kind of recap, remember, you've got multiple paths once you get to this point. Once you write this equation right here, and this equation right here, you've got multiple paths to take, right? So this t is this t over here, right? And so we treated this question to be, well, what happens if I wanted to find the total time? Okay, Or I can treat this question to be, okay, what happens if I want to do the max height time first, and so forth, and kind of follow my order in my question, okay? And I'll do that here in the next video.